Hello, this video is for the solutions for the review packet for the final exam. Just a reminder that this packet doesn't cover all the new material, so make sure that you're working on the practice finals so that you see a wider variety, but this will get you some practice at some of the problems on pencil and paper. And then remember that the old stuff is coming from the old exams with the numbers changed, so make sure you're working on your rewrites for those old exams and studying those solutions as well. All right, let's jump into the first problem. The table to the right gives the popular vote that counts in millions for two leading candidates in a presidential election. Draw a two-circle Venn diagram that represents the results. And then we have this contingency table over here where we know the gender of the voters and then whether they voted for candidate A or candidate B. So for the Venn diagram, we want to start off with a rectangle. That rectangle should represent everybody that's in the table. So let's say that that is voters. And then we want to draw two circles in there. Go ahead and bring some color in. So I'll do a green circle and kind of a teal circle. And then we want to label these so they encompass everything that's going on in this table and then put the numbers in there as well. So one of these tables should be for gender, or sorry, one of these circles should be for gender and the other circle should be for the candidate. So let's go ahead and make the green circle for gender. Since women are first, I will make that the women circle. And then when we go to the candidate, because candidate A is first, I'll make that what this circle represents. So I'll just put an A in there. So the common mistake is for people to want to do a circle for women and a circle for men, or a circle for A and a circle for B. But you do a circle for each variable. So a circle for gender and a circle for candidate. And then recently I realized a trick that you can do that makes filling in this Venn diagram super simple. Since the women's circle is in green, let me come over here and circle the women's row in green. And then I'm going to do the same thing for candidate A. Since that's the teal circle, I'm going to circle candidate A with the teal circle. And if you were to do that, and then draw a box around it, you've essentially got your Venn diagram right there. So the intersection of the green and the teal should represent women and candidate A, so that 38.35 would go right here in the overlap, and that's a little bit of a small area, so I'll go ahead and label that off to the side like this. Probably would have been better to draw the circles so the overlap was a little bigger, but if you do ever have a small space to label, this is one way that you can handle it. And then for this part of the circle, so let's think about what this is. It's circled in green but not in teal. So circled in green right here but not in teal would be 27.13. And then let's just think that through. Those should be women who voted for candidate B. They're women because they're in the women's circle. And they voted for candidate B because they're not in the candidate A circle. And then this area here would be circled in teal but not in green, so that would be this 29.16. And then thinking about that one also, let's just think about it in terms of this picture. They're men because they're not in the women's circle and they voted for candidate A. Does that match what it says over here? Yep, they're men and they voted for candidate A. And then this number right here is not circled with either color, so that would be the outside of the circles area, 28.98. And let's just think about that in terms of the picture, kind of not looking over here and thinking, who are these people? Well, they're not women, so they're men, and they didn't vote for candidate A, so they must have voted for candidate B. So these must be the men who voted for candidate B, and we see that that is correct. So that's a nice little trick to make these Venn diagrams easier from contingency tables. If you pick your variables and which item you want to use, so I used the women because they were first and candidate A because it was first, but I circled them there and then that matches up with everything I'm doing in the circles in the other spot. So a nice little trick to make the Venn diagram problems nice and fast and easy. All right, moving on to problem 2. Let's match the given information to the appropriate histogram. They say the mean is 35 and the standard deviation is 2.6. So let's think about drawing in the mean first. So 35, let's see, this looks like a scale of 5. So 35 would be right about here. There's no way that can be the right answer because the mean is a type of center for data and you can never have all of your data on one side. So we can rule out that one. Same thing here, just looking at these numbers, if you put the 35 on, that's right about here. All the data's to the right. There's no way that can be the right one. If you look at this one, 35's kind of in the middle, so that seems reasonable. But if you look at this one, 35's kind of right in the middle. So both of these graphs are still in contention if the only thing that you were to consider was the mean. But they also told us the standard deviation. So what we want to do with that is use the idea that most of your data set will lie within 2 standard deviations of the mean. So let's make a calculation where we take the mean plus or minus 2 times the standard deviation. So that would be 35 plus or minus 2 times 2.6. And again, according to the empirical rule, you should have about 95% of your data within 2 standard deviations. So let's see what these boundaries are. Let's see what you'd get with a minus and then what you would get if you did the plus. So let me bring the calculator in for that. So we have 35 minus 2 times 2.6 is 29.8. And then I'll just hit second enter to pull that back up and change that to a plus sign, and we get 40.2. So the right answer will be the picture where you have most of the data, about 95% of the data, in between 29.2 and 40.2. So on this picture, 29.2, this is 20 and 30, so 29.2 is maybe just before the 30, like around there. And the 40.2 is just past the 40, so maybe about there. I think that's going to probably be our correct answer because most of the area of those bars is in between the 2 lines. But let's check the other picture too. If I drew in 29.8, that'd be right about here, and then 40.2 would be right about there. There's a decent chunk of the area in between those 2 lines I drew, but no way that's 95%, because if that was 95%, this leftover part's supposed to only be 5, which should look really tiny, but there's a huge amount on the left that's not in between the blue bars. There's a huge amount on the right that's not between the blue bars. So this data set is more spread out. It must have a standard deviation bigger than 2.6, but this one, more tightly packed together, looks like it has 95% or most of the area between my blue bars with just a tiny bit on the outsides, which could be the leftover 5%. So if we were doing the multiple choice, I would fill in that bubble right there. So I choose C for that one. And circle that bigger, just make it more clear. All right, moving on to problem number 3. What is the probability of not rolling a sum of 4 with 2 fair dice? Since they're asking me a question about the sum, I want to go ahead and make a table where I list all the sums. So make a vertical and horizontal line, and then you don't need to think about color on this necessarily, but I'll go ahead and think about the die across the top as a green die, and the die down the side will be a red die. So 1, 2, 3, 4, 5, 6. So I'm listing the possibilities for the red die and the green die, and then I just want to think about what are all the different sums I can get. So I'm going to start adding those up. So 1 plus 1 is 2, 1 plus 2 is 3, 4, 5, 6, 7. 2 plus 1 is 3, and then 4, 5, 6, 7, 8. 3 plus 1 is 4. 5, 6, 7, 8, 9. 4 plus 1 is 5. 6, 7, 8, 9, 10. The 5 plus the 1 is 6, 7, 8, 9, 10, 11. And then finally the 6 plus 1 would be 7, and 8, 9, 10, 11, 12. I use patterns to make this go faster. But the reason this is a 9 is not because it's after 8 and before 10. It's because the red die is a 5 and the green die is a 4, and 5 plus 4 is 9. So all these numbers out here in the body of the table are sums of the top number and the left number. So what do they want us to do? They want us to do the probability of not rolling a 4. So the probability of not getting a 4. So we can use the idea of the complement rule here and say that will be 1 minus the probability that you would roll a 4. So if I can find the probability of a 4, I can just subtract that away from 1, and that would answer the question. So how many ways are there to roll a 4? Looks like there are 3 of them. Red 3, green 1, a 2 on each die, or a red 1 and a green 3. So 3 different ways to get that out of, if you count up all the possibilities in the table, there's 36 because it's 6 by 6. So I have this 1 just carried over, minus the probability of rolling a 4, which is 3 out of 36 possibilities altogether in the table. We can go ahead and get a common denominator for the 1. That would be 36 over 36, which is still 1, but has a common denominator with the other piece. And then that is equal to, let's see, 36 minus 3 is 33/36. If this is on MyMathLab, they might ask you to reduce it. You could cancel a 3 top and bottom and get 11/12. If it's on the final exam, I would rather that you went to a decimal. So if we're going to a decimal, the reducing step really isn't necessary. We could just do 33 divided by 36. I will ask you to round these to 4 decimal places on the exam, so I'll do that here, 0.9167. MyMathLab often does 3 decimal places, but just pay attention to the directions on that. And notice if you don't reduce it, you get that decimal. If you do reduce it, you get the same decimal. So if you know you're going to a decimal, then the reducing step is kind of a waste of time because you could just go to the calculator right here. But again, there are some MyMathLab problems that ask you to give your probabilities as a simplified fraction, and by that they mean a reduced fraction. So there will be times where you need to do it this way as well. All right, moving on to number 4, we're going to practice using the empirical rule with a normal distribution. Assume that a set of test scores is normally distributed with a mean of 75 and a standard deviation of 10. Estimate each of the following quantities and show your work, including a sketch of the normal curve. So they want to know what the percentage of scores that is higher than 75 will be. So I'm going to start off by drawing in a bell-shaped curve, and then we want to drop down from the center, and that should be our mean. And the mean of this curve is 75. So normally I would notch out 3 standard deviations in each direction because that would help me use the empirical rule, but I noticed the boundary that they're talking about, the 75, is my mean. So let's go ahead and shade that in real quick. The percentage of scores that's higher than 75. So this one doesn't actually use the empirical rule specifically. If you just look at the curve, the mean is at the center. On any symmetric curve, you have your mean at the center. And that also means you're going to have an equal amount of area on both sides. Well, we know the total amount of area under the whole curve is 100%, so if we have exactly half of that curve shaded, then that area right there needs to be 50%. So that is our answer, and that one doesn't really use the empirical rule. It just uses the idea that the total amount of area under the curve is 100%. We've shaded exactly half of that, so that gets us to our 50% number. All right, let's move on to the next one. Let's find the percentage of scores that are less than 65. So I'll start off drawing that bell-shaped curve again. I'll once again drop down from the middle and label that as 75. And then this time 65 is not that number, so I want to start thinking about my standard deviation, which is 10, and I want to use 1, 2, 3 of those to reach the edge of the curve, and 1, 2, 3 of them to reach the other edge. And each notch, when you're using the empirical rule, you want to be measured out in terms of the standard deviation, which in this case is 10. So 75 plus 10 is 85, plus 10 is 95, plus another 10 is 105. And then starting here and subtracting 10, 75 minus 10 is 65, and then 55, and then 45. And then let's think about what they're asking us to find, the percentage that is less than 65. So I'm going to draw in that border at 65, and then it's less than, so I'm going to shade to the left. So whatever that area is right there, that's going to be the percentage, or at least I can, I'll make the percentage out of that. And then I do want to point out that that shaded area doesn't stop at 45, it goes forever to the left. It doesn't say from 45 to 65, it says less than. So we'll go right on past 65 and keep on going. All right, so how do we find that area? Well, what you need to take advantage of on these curves is the symmetry and the empirical rule. So we went over one notch to the left, so I'm going to draw one notch to the right also. I'm not going to shade to the right because they didn't ask about more than 65, but to incorporate the empirical rule into this, I need that symmetry. So if I have a boundary that's one standard deviation to the left, I'll also draw in one to the right. And then we've got to know the empirical rule. The empirical rule says if you go out to both sides, 1 standard deviation, that's about 68%. If you go out 2, it's 95%. And if you go out 3, it's about 99.7. And if you go out forever, it's 100. All right, so we're going out 1 standard deviation here, 1 notch in each direction. So this area in the middle is 68%. Now it's not the area we want, but it can help us find it, because we know the total area under the curve is 100%. We don't want this area, so I can subtract that away, and that gives me 32% left over. But I know these curves are symmetric, so the amount of area past this line, which is 1 standard deviation away from the mean over here, must be equal to the amount of area over here. So this leftover 32% is the total of this area on the left that I do want, and this area on the right that I don't. But if I wanted the area of each individually, I would cut that in half, and 32% over 2 is 16%, so that's the amount of area on each side. So the amount of area right here is 16%, and the amount of area over here is 16%, and this is the area I want, so that's the answer to my question. All right, let's move on and try the last one. Let's find the percentage of scores between 65 and 95. So just going to start off drawing that picture again. So I'll do it a little quicker this time. It's the same idea. Didn't come out as bell-shaped as I would have liked, but that's okay. So 75 in the middle, and then 1, 2, 3 notches to the flattening out would be 85, 95, and 105. And then 1, 2, 3 notches out to the flattening out spot on the left would be 65, 55, and 45. And then I want to show what it is they're asking us to find. So they're asking us to find the part between 65 right here and 95, which is right here. So I'm going to put those two boundaries on, and then I'm going to shade. All right, so somehow I have to use the empirical rule to figure this out. But if I'm going to use the empirical rule, I want to take advantage of symmetry. But these boundaries aren't symmetric. This is 1 notch to the left, or 1 standard deviation. That's 2 notches to the right, or 2 standard deviations. So I'm going to artificially kind of draw in the symmetry. Since I have 1 notch to the left, I'm going to do that right here. And say if I go 1 to the left and 1 to the right, just like above, that's 68%. But that's not the answer. That's too small. I need that plus whatever this piece is over here. So I have to try and figure out how much that piece is. So let me draw a symmetric line to this 95. That's 2 notches to the right. So let me go 2 to the left and draw in a line right here. And if I went between those two, since that's out 1, 2 standard deviations, according to the empirical rule, that would be 95%. But 95% is too much. That has all the stuff I have shaded in blue, but it has some extra. All right, so how do I get at that? Well, let's do some math. If I take the 95% and I subtract the 68%, that gives me 27%. So what is that 27%? I took the area from here to here and subtracted out the middle. So that 27 represents this chunk right here on the left that's not shaded, and this little piece right here that's shaded in blue. I want this piece, but not that piece, so I need to separate those out into the individual sides. Well, we have symmetry, so each of those sides is equal. So take the 27% and cut that in half, which is 13.5%, and half of that goes here. So this is 13.5%, and the other half goes right here. But what part do I want? This is why we shaded the graph to begin with. I shaded the part I wanted in blue, so I want this part, which is 68%, plus this part over here, which is 13.5%. So the total of my blue area, which is what I want, is 68% right here in the middle, plus this 13.5% on the right-hand side, for a total of, let's see, I believe that is 81.5%. So that's the trickiest case, is when you don't have the symmetry. So you have to kind of artificially create it. If one boundary is 1 standard deviation over, then draw one in 1 standard deviation to the other side, even though that's not one of your boundaries. So you can bring in the empirical rule and do the same thing with the other number. And then you're going to have to play around with how do I break that up to get the pieces. And with practice, it becomes easier. It can be a little tricky at first. A lot easier if you just need one set of boundaries and use the empirical rule once. So this is kind of the messiest case where you'd use it a couple of times. All right, let's go ahead and move down to number 5, a probability question about a spinner. So consider the spinner shown to the right. Determine the probability that the spinner would land on a 3, or the probability that we would end up with an odd, or at most a 4. All right, so in order to make these problems work well, you'd like every region to be the same size, because there's a temptation to say, okay, there's 4 regions, so the probability you'd land in the 1 is 1/4. But you can see if you look at this, that 1 is half of the circle, not 1/4 of the circle. So what you want to do is create symmetry. So, and equal size. It's kind of like getting a common denominator, essentially. So if you look at this one cut in half, if I cut this in half, they'd be equal size. Extend that through, and I extended this one through, extend this line through. And the key is that all of your wedges be the same size. And it looks like they are. And then how many are there? 1, 2, 3, 4, 5, 6, 7, 8. So each of these pieces is 1/8 of the circle. And in order to calculate probabilities accurately, you need to have equal size pieces. So the spinner, what's the probability the spinner would land on a 3? Well, 3 is right here, and that is exactly one of our wedges out of 8 equal sized wedges. So that would be a 1/8 chance. If they wanted a decimal for that, we could divide 1 by 8, which is 0.125 exactly. So I'll go ahead and give that decimal answer. Again, my math lab might ask for the fraction. Either one is okay. Just make sure that they're both right, is what I should say. Just make sure you're following directions. Do they want a fraction? Do they want a decimal? And again, notice if I hadn't drawn the equal wedges, I might have said 3 is just one portion out of 4. But you need to be counting equal size portions. All right. This next one's a little tricky. We're going to do the probability that the number is odd or it's at most 4. So let's think about what numbers that would be. So what are the odds here? Let me just go with black. So what are our odd numbers? That would be the 1 or the 3. So we want to count those. And then what are the numbers that are at most 4? Well, at most 4 is 4 or fewer. So at most 4 is actually 0. Whoops, there's no 0 in the spinner, sorry. 1, 2, 3, and 4. That's everything. When you do an OR, if you think back to Venn diagrams, if you're doing an OR, you're supposed to shade all of the first one, and then whatever's new from the second one. So what if I employed that same philosophy there onto the spinner? So I'd want to shade the stuff that came first in green. So that would be the 1s. And the 1s are all 4 of these wedges on the left. And then the 3, which is this wedge that I already had shaded in black. I'll add the green shading to that. But then, according to this, you're supposed to go to the second one and shade everything that's new. So I've already shaded the 1 and the 3, but if I shade the new stuff, that would be the 2 and the 4. And then if you ask the question, what's shaded? It's actually everything. How many wedges? 8. But out of how many? 8. So this would be 8 over 8, which is 1. And that's kind of tricky just because you don't expect that to happen. When somebody asks you a probability question, you expect it would just be part, not everything. But even if they just asked what's the probability it would be at most 4, that would be everything because it was already 1, 2, 3, 4. So it's all 8 out of the 8 equal sized wedges. All right, moving on to number 6. The table gives the gender and political affiliation of 100 randomly selected voters at a voting site. Suppose you select a voter at random from the site, and then they have a bunch of probability questions for us. So we've got a contingency table. We have 2 variables, gender, and then we also have political party. And when you're going to do probabilities, you really want to have totals on here as well. So they didn't give them, but I'm going to add them on. So if you add up the 26 women that are Republicans and the 27 women that are Democrats and the 7 independent women, you get a total there of 60. If you add up the men over here, you get a total of 40. So the grand total is 100, and we often use the grand total in our probabilities, so that's an important one to know. But we also need to know the total number of Republicans, so we add up the men and the women there, and there's 47. And for Democrats, we add up the men and women, and there's 37. And for the independents, we add up the men and the women, and there's 18. Now, it should be the case that if you add this way, you get 100, and that wouldn't happen, so I just realized I made a small mistake there. 7 plus 9 is 16. And then if you add up this vertical way, 47 plus 37 plus 16, you will see that that's 100 as well. Okay, so the totals are going to be really necessary when we do the probability, so you might as well, when you see a chart like this, and you know they're going to start asking you probability questions, get those totals thrown on there. You're definitely going to need them. All right, so what is the probability that you select a man? So the probability that it's a man. Well, there's no given on there, so we're going to use all the people in the table, which is 100. And then we're just going to count all the men in the table, so we want the total for men, which is 40. So 40 over 100, which if we went to a decimal, is exactly 0.4. What's the probability you select a Democrat? Same idea. Probability that it's a Democrat. There's no given in that, so the grand total will be our denominator. And then we'll count all the Democrats, so the 27 women plus the 10 men for a total of 37. And then we'll switch over to a decimal, and because we're just dividing by 100 in this one, which is only because that's the grand total, so be careful with that. If the total is 184, then you would divide by 184, and it would be messy, so you'd go to your calculator. But dividing by 100 is kind of nice. It just moves the decimal over a couple notches, so that would be 0.37. And then let's start looking at some other types. Let's see, what's the probability that you select a female independent? So they didn't really say this, but when they say female independent, that's saying that the person has both traits. So they're really saying that it's a female and she's registered as an independent. So they didn't use the word and, but it's really part of that. When you say it's a female independent, you're saying it's both traits, and that's what an and does. So that's what we're really after, probability that it's a female and she's an independent. So we're looking for overlap, because that's how we do and questions. So let's see, let's bring in the teal for that. So we want female, and then we also want independent. And then when you're doing an and, you want the overlap. So then how many voters are in the overlap of women and independent? 7. And there's no given in that question. So 7 out of how many? Out of the grand total. So 7 out of 100, which if we move the decimal over 2 spots would be 0.07. So I would highly suggest that you do what I just did there. When you are working with a contingency table and you have an and type question, circle both variables and then look for the overlap. That'll be your numerator. Grand total will be your denominator. All right, let's look at the next question. What is the probability that you select someone who is a female or a Republican? So very straightforward on the wording this time. It has the word or right in it. So we're looking for the probability that it's female voter or Republican. All right, so how do you do that with the Venn diagram sort of thought? What do you do with an or? So the idea, like we saw on previous problems, is all of the first one and then add in whatever is new from the second one. So just to bring in a different color this time, I'm going to go up there and circle in green. So I'm going to circle the females. Actually, we already had the women circled, but I'll recircle that in green. And then the Republicans, which I'll also circle in green. All right, so now let's think about the shading that we did down here. We want all of the first one, so that was the female voters. So we want these 27 or 26, these 27, and those 7, all of them. So that's 60. So going back down here, out of the 100 total, we want all 60 of the female voters. Plus, according to this picture, we're going to add on any from the Republican group that we haven't already counted when we counted the females. So since I shaded that red here, let's go do that up above. So you want all the Republicans that you don't have already. Well, we already have these 26 counted as part of the 60, but these 21 right there we haven't counted yet. But according to this, after you count all of one, you count anything that's new from the rest. I'm not going to use the total this time because I'd be recounting the 26 women. I just want the Republicans I haven't counted yet, which would be those 21 men. Go ahead and add that in red just so we can kind of remind ourselves where it came from. So we end up there with 81 out of 100, and running out of space, I'll do the division in my head, which is just going to move the decimal over 2 spots. So 81 divided by 100 would be 0.81. So when you're doing an OR, you want to count everything from the first, so all 60 women, and then whatever's new from the second, so just the Republicans we hadn't counted yet, which in this case would just be the male Republicans, and then add that together, and we get our answer. All right, and then the final question on this one, what is the probability that you pick a Republican given that you picked a male? So what's the probability that you get a Republican given that it was a male that you picked? So givens are a little bit different. This is the one case where we don't use the whole table. You just try and reduce the table down to the part that is the given. So if they say the given is male, then we only want to answer this question looking at the people in the table that are male. So we're not going to look at the whole table to answer this. We're only going to look at the part that has the men in it. So that means we're only looking at the part that has 40 people in it. Or 40, there's 40 men, but like just those 40 people are being counted. So instead of out of the whole table, we're only answering this question out of the 40 that are male. And then when we go to think about the front part of this, the Republican part, we have to think the same idea, that we're only looking at those 40 men. So if you only looked at those 40 men, how many are Republicans? And that would just be those 21 right there. You wouldn't say 47 because you're supposed to only be looking at the men. So you're not counting these 26 women Republicans, just the 21 that are men. So when you're doing conditional probability, you always want to start with the given. I would highly suggest circling it like I did here and saying I can only use numbers from this when I answer this question. That's how givens work. They reduce us from the whole table just to a part of it. So if we can only use this part, the total is 40, and the part that is Republicans are those 21, so 21 out of 40. And then just finishing that off, this isn't a nice simple move the decimal over, so I'll go ahead and do the division on the calculator. 21 divided by 40 is 0.525, and that would be the answer. All right, again, this is just a few questions and some practice on pencil and paper. Make sure that you're working on those practice finals to see other types of questions that could be on the final exam. Make sure that you are also practicing those old exams so that you're ready for any old questions. The numbers will be changed on those, so don't just memorize the answers. Try and make sure you understand how those problems are done. All right, hope this helped, and good luck with your studying and on your final.